Hi, I'm Farak Masood. I went to the Cavan School of Mines. I represent Oberon Solutions Australia. At Oberon, we offer a full 360-degree, sector-specific answer to all your contractor management, recruitment, HR, payroll, governance and legislative issues. Let Oberon Solutions Australia take the pain away so you can focus on the projects that will move your business forward. Search Oberon Solutions Australia.
Good evening or good morning, wherever you are in the world. My name is Nick Beaton, and I look after the Integrated Extraction Simulator program for CRCOR. I'll just give you a couple of minutes on what CRCOR is and what we do, just in case you're not familiar with us, and then we'll get into the new advances that we've made in simulating metallurgical processing. So CRCOR is an industry funded body, and we have three main stakeholders in our organisation. The mining companies who fund us, and you can see their names there on the left-hand side of the screen. You can see the METS companies there, that's the mining equipment technology and services providers, who are also funders of CRCOR. And then you can see our research collaborators that we work with to perform the research which forms our work. Now, our work consists of three main pillars. The first one is grade engineering, so more commonly known as pre-concentration. And what CRCOR has done is bring a formality and a measurement process to grade engineering so that mine planners and geologists and metallurgists can understand the deportment of mineralization to, for example, different size fractions in an ore body, and then use that knowledge to be able to exploit the ore body more appropriately by sweetening the grade that goes to the processing. That's where the integrated extraction simulator comes in. And the integrated extraction simulator is our cloud-based simulator of grade engineering and all of the other processes in mineral processing so that we can understand and predict what is going to happen as we exploit the ore body. Our third main pillar is, of course, technology transfer and training, and making sure that this technology and the things that we have devised and invented are brought to the world appropriately. Now, let me turn my attention here to the integrated extraction simulator itself. So the integrated extraction simulator is a cloud-based simulator. So we mount it on Amazon Web Services, or AWS as we call it. And it enables us to simulate the entire mineral processing chain. And as you can see on the screen there, all the way from drill and blast through comminution to the final concentrate. So this is a very, very wide, a very broad expression of the value chain. And we've brought some advances to this, and I've just written them there. So we have brought mass simulation into the equation. That means using the power of the cloud to be able to do millions of simulations of different scenarios in order to cover and understand the problem space. We've brought circuit optimization into the simulator so that we can actually make sure that the circuit, the flow sheet, is producing at its best potential. We've also introduced constraint management. This is a very important part of the integrated extraction simulator because it allows us to make sure that the simulations that we do are actually feasible in the real world, because we put in all of the real world constraints. And this allows us to do very comprehensive and very high fidelity scenario analysis of different mining processes. So let's have a look at the sort of things that we look at in IES, in the integrated extraction simulator. So let's start with having a look at this flow sheet. So this is a screenshot of the screen of the integrated extraction simulator, showing a flow sheet starting with blasting, going to primary crusher through to a SAG mill. And then that SAG mill is in closed circuit with a pebble crusher. So the oversize coming out of the SAG mill is crushed and returned into the feed. That goes on to a ball mill flash flotation and a rougher float, and then into a regrind mill, cleaner flotation circuit and scavenger flotation circuit through to the final concentrate. So quite clearly that's a very straightforward SABC, as we call them, a sag mill and ball mill configuration in enclosed circuit. And when we press the blue simulate button, which I've simulated there with the blue simulate button, when we press that in IES, it sends all of the data in the front end up to the cloud and starts processing the material that we find in the block that is being blasted, passes it through the chain all the way through the different pieces of equipment, and calculates what every piece of equipment and what every connecting stream, so they're the blue lines between the equipment, it calculates what each one of those will look like in steady state. So I'm just going to go to the next slide. And so we get analysis like this. So what you see there is actually a size fraction.
Screen.
I'm sorry. Okay, hang on just a second. I do beg your pardon. So I wasn't sharing the screen. Let me go a little bit back then, see if I can catch up on a little bit of lost time here. What I was showing here was an SABC circuit, so a sag mill circuit, and starting all the way from blasting, primary crusher, pebble crusher enclosed circuit with that sag mill, going through to the ball mill, flash flotation, rougher float, regrind, cleaner scavenger, and then down to final concentrate. So sorry for not having the screen working properly there. That's entirely my fault. So what we can see now is when the simulator calculates what happens to the material, it gives us a lot of analysis, and we can see there, oops, let me just go back. We can see there in those colored diagrams, those are size fraction analysis showing us on the x-axis the size fraction that is passing through that piece of equipment, and on the y-axis the amount of mass, and those histogram, the colored histograms show us the material that is passing through there. And you can see, let me just go back a little bit, as we pass through the circuit, the material is being liberated. You see other colors coming in there at the low size fractions, which represent the minerals which have been liberated. And then we come to the final concentrate, where we have the main mineral that is our target, in this case, chalcopyrite. And then we have all of the information for all of the streams. So this is an enormous calculation, and we use the power of the cloud to be able to do that. Okay, let's now have a look at some of the advances we've made, because you'd expect a metallurgical simulator to be able to do those types of calculations and to do them very efficiently. The advances that we've made in IES, which make it now unique, is, and I'll start here, with mass simulation. So if we take a block model, so this little blob of, let me just highlight this. So this little blob of color here, this is a block model. And this block model, the different colors represent different geometallurgical responses there. And that can be expressed as a CSV file, which is this little document here, which as you'll be familiar with from Excel. So if we convert the block model into a CSV file and we have all of the geometallurgical parameters, we can process those through a flow sheet, and it will calculate for each block in the block model. So each block is represented by one of these rows in the block model. It will then go through that, and it will process each one of those blocks in the block model and write relevant information from that into that CSV file. So that's denoted by this blue box here. And that information, the important information there, would be, of course, the throughput and the recovery energy consumption and water consumption. So we can do that for every block in the block model and get an extremely high resolution understanding of the geometallurgical response of the ore body. Now, when the user does that, let's have a little bit more of a look at that in a practical sense, right? So what I'm going to do here is just move us to the next slide. So I've replaced the flow sheet there with what's happening actually on the AWS server. So I've got some example customers there that we work with: Teck, Anglo Gold Ashanti, Anglo, BHP. They all have their own separate environments. And let's say that one of them now wants to process that entire block model. So on the back end, as we call it, on the cloud, what would happen is the user would fire up multiple CPUs. So this is multiple cloud servers, and each one of those servers would take part of the load of processing that block model and write the answers back into the blue box on the right-hand side. So an extension of each record. Now, I've shown here just a dozen or so CPUs. For a very large job, that would normally be something along the lines of around about 3,000 to 4,000 servers, which you can run for a couple of hours at quite modest prices on AWS, and then you just release them back to the cloud farm that they have, and you no longer pay for them. So it's a very, very efficient way of getting a lot of computing power. Now we can take this, this now modified block model that we have here with throughput and recovery in it, and we can load that back into a general mining package, and we can view the metallurgical response. So this is a heat map. We're looking at an ore body there, and you can see the little voxels, the little cells. Each one of those represents about 100,000 tons of material. And the red material is material that we're interested from this simulation. In this particular case, this was a mine to mill simulation. So we were looking at the effect that intense blasting had on throughput and recovery. And so the red areas of the block model of the ore deposit, they represent areas that would be amenable to mine to mill intervention. And then the blue areas, for various reasons, including the fact that the material might be quite soft and therefore not really benefit from harsher blasting. So we can have a look, and we can then use this in the mine planning. Now, we've also used this in design review mode. And for instance, what I have up on the screen here is looking at different concentrator designs and then seeing what the response would be like for the concentrator, for different concentrator designs, right? And you can see there that the concentrator on the left, which was the previous view that we had on the single screen, that is showing that there is amenability to mine to mill intervention at quite some extent there in that southern end. And then the concentrator number 3, that has less amenability for mine to mill treatment. So we use the mass simulations for doing very comprehensive scenario analysis. Let me now move on to one of the other things that we have brought to this process, and this is optimization. So in IES, you can configure a flow sheet, you can tell the system what material it is processing, press the blue simulate button up there, and it will tell you what will happen to that material in this flow sheet and everywhere along the flow sheet. What you can also do is actually flip a switch, literally this switch down here, enable the optimization. And instead of telling us what will happen to this material in this circuit, what it will do is it will actually optimize the circuit and tell us what is the best that we could get from that circuit, and indeed what we could, what the operational settings would be required to achieve that. One of the kind of hidden gems of IES in that process is constraint management. So the constraint management enables us to look at the real world constraints in that flow sheet and say, all right, I know that this pump, this conveyor belt, this pipe here has a particular constraint. or has a particular power limitation, we can put all of those constraints into the optimizer. And so now we know that every optimized solution that we get, and remember, we're still doing this for every block in the block model, every optimized solution that we get is actually possible in the real world, right? Now, I notice here on the chat thing that I've got a question come up here. So let me see if I can just have a quick look at that. Comment on how the simulation accuracy was validated. Usually there are assumptions about best efficiencies, but these are not real. Is the extraction process diagram dynamic, allowing one to view the data changes? Okay, so those are two questions. The first one about the validation is a very important part of IES, and thank you for the question there, right? So the first one's very important. At CRC-OR, we have built the IES integrated extraction simulator to be a little bit like the iPhone that consumes apps. So we've built the platform, the iPhone, but the models for simulating each individual metallurgical process, crushing, grinding, flotation, separation, those are actually built by equipment manufacturers and, more importantly, researchers around the world, and they've been validated in their research programs. So IES has been built to be quite neutral to the models that it takes. And one of the things that we did in the architecture of the system when we built it was make it very easy to import models from various sources and to provide users with a very diverse range of models that they can use. And we have a little bit of a saying, which is the best model to use is generally the one for which you have data. Now, the mainstay of IES is by far the work that's been done by the Julius Krutschnitt Mineral Research Center, and also through the IMARC projects that have supported that for many decades. Of course, we have building a big library of other models, but the mainstay of this is the work that's been done by the JKMRC. Is the extraction process diagram dynamic? That was the second question. I think the best answer to that is yes, it's dynamic, because when we actually feed those individual rows of the CSV file into the simulator for simulation, we not only put in the material properties, we can also dynamically change the configuration of the circuit. So as the circuit gets modified over the life of mine, the system can actually respond to that. Okay, what I'm going to do now is just have a quick look at the future of IES. I think I'm running reasonably on time. So the future of IES, where are we going with this? Because I want to leave a couple of minutes to be able to show you a video. First of all, we're transitioning to sustainable commercial operations, and we're going to do that by the middle of next year. So we're already in discussions with parties of how we take this out of the research mode and bring it to commercial operation. That will mean, of course, that we'll expand the user base beyond our participants and the sponsors of the IMARC P9Q project who funded the development of IES. But we'll continue, obviously, to work with research institutes and equipment manufacturers and so forth to implement new equipment models as they come to fruition. And one of the things that we've been working on is our ability to build models out of the data that has been captured in plant information systems, so that we can actually fuse together the physics models that have been developed over many decades with models that come from data sources and that are built using regression techniques. And the one that we use mostly is we build our models out of neural networks. And it is completely possible to build artificial neural network models into a flow sheet that also has physics models. And we've shown time and again that this is a very successful combination. I'm just now going to show you a quick video to complete this presentation, and it'll take you through some of the aspects of IES. Let me just do this. Bring up. There we go. As we consume more metal, the mining industry has to develop increasingly complex ore deposits. We need innovative and very sophisticated techniques to help solve the engineering problems that this throws at us. CRCO identified that one of the obstacles to solving these engineering problems was the integration of all of the processes and pieces of equipment in the value chain. And IES sets out to simulate all of these processes in a very detailed. Let me just see if I can restart the video from where more or less where it left off. There we go.
Anglo-American is the diversified miner. Our purpose is to reimagine mining to improve people's lives. Our burning ambition is to be the most valued mining company in the world by 2023. And we see using tools and technologies like IES as a core and fundamental part of the whole optimization process going forward.
In Anglo-American, we have implemented IES in the Bronces copper mine in Chile, which is a very significant outcome.
So far, we've achieved about a 5 to 6% uplift in value. That's significant from many perspectives. It's increased revenue, and secondly, its increase in revenue has come at very low capital costs.
In 1965, it was Lercher-Grodman's algorithm which changed the way that pit optimization was done. In 1988, it was Kennedy creating the cut-off grade optimization theory. Now, the IAS is providing the new era, integrating not only the ore feed, also the processing output. It's bringing a lot of simplicity to the optimization process.
Hi, I'm Farak Masood. I went to the Cavan School of Mines. I represent Oberon Solutions Australia. At Oberon, we offer a full 360-degree, sector-specific answer to all your contractor management, recruitment, HR, payroll, governance and legislative issues. Let Oberon Solutions Australia take the pain away so you can focus on the projects that will move your business forward. Search Oberon Solutions Australia.